Hello biology. This is Bio Assist to Your 101, and we already started something on this course. We are doing biophysics. This is the second episode on what we did last time. Last time we did an introduction to biophysics. We looked at the macromolecules. We looked at scientists, the ways they have developed in viewing macromolecules such as nucleic acids and proteins. And we said that some of them use gel electrophoresis, some have developed radio tracing in order to view DNA. So that was what we did last time. And today we want to look at how the idea of genetic composition, or how DNA looks like. Who they started to develop the idea of DNA? Who started to give the fair idea of DNA? So we look at the experiment on the nature of DNA, or genetic material by Frederick Griffith. He was the scientist who started the whole process that led to the discovery of the DNA. So later we'll come to look at other scientists, their work, and how they helped to discover DNA. But we can't move on without looking at this man's experiment, which is Frederick Griffith's experiment. So let's start by looking at Frederick Griffith experiment. So Frederick experiment. So in those days, there was pneumonia happening rampantly. The disease pneumonia was occurring, and the causative organism for pneumonia is Streptococcus pneumonia, or pneumococcus. Streptococcus pneumonia or pneumococcus. So that's the causative organism for pneumonia. So they are bacteria. And we had 3 strains of pneumonia. We have the type 1, type 2, and type 3. But in his experiment, he used the type 2 and the type 3 strains. So the type 2 is the rough strain, and the type 3 is the smooth strain. And looking at their morphology, the smooth strain has a capsule around it, which helps it to cause disease. We know that from microbiology, the virulence of the organism depends if it has a capsule. When it has a capsule, the blood cells, the immune system, it finds it difficult to kill it or lyse it. But when it's without a capsule, that is when it is easily removed by our immune system. So the virulence of the organism depends on the capsule. So with a smooth strain, it has a capsule, but with the rough strain, it has no capsule. So meaning that the rough strain isn't able to cause disease in animals, and the smooth strain is able to cause the disease pneumonia. So now let's move on to let's see this first section over here. So this was what he did first. Firstly, what he did was that this is the S strain, the smooth strain. It is live, it is living. So here they are, and it has a capsule, so it's indicated here. So he injected this bacteria, the smooth strain, into the mouse, a living mouse. So within days, the mouse developed the disease, so the mouse died. So we can see here that this is the mouse. The effect is that the mouse died. So that's what he did at first. And what he did secondly was that we can see over here, this is the rough strain, the out strain, which we said initially that it doesn't cause disease. So it has no capsule as indicated over here. So what happened was that he injected this live out strain into the mouse, and truly the mouse didn't die, because the out strain is not able to cause any disease. So the mouse still lived on and on and on. So our next one here, he did something very interesting over here. What he did was that he heated the smooth strain. We can see over here that the smooth strain is over here, and he heat killed them. So in the test you realize that he has heated the smooth strain over here, and they are all dead. So when he now injected the smooth strain into the mouse over here, the mouse continued to live. Why? Because when certain bacteria are heated, when they are heated, they don't enjoy very, very high temperatures. All bacteria have their temperature ranges. So pneumococcus is not a hyperthermophile. It is a mesophile. So it was not able to withstand the heating, so it died. That is why it wasn't able to cause any disease over here. So we can see the mouse still alive over here without the disease. So the mouse is still alive here. So let's see the last section. the last section. So what he did was that he heat killed the heat strain, the air strain. Okay, the air strain. So you realize that here it's heat killed. Okay, heat killed air strain, and just as he did over here, that's the same thing that he did over here. But this time he did something in addition to it. He puts the heat killed strain into a test tube. Okay, and now what he did was that he added the live strain that does not cause disease, that is not supposed to cause disease, as in this place. So he added the live strain to the test tube where the heat killed air strain was. Okay, and later he injected what he got into the mouse. But we realized that after some time the mouse died. So what is causing this kind of transformation? We realize that there is a transformation going on because the smooth strain here, okay, when it is heated and killed, it is not supposed to cause disease, as we can see over here. But this time when it is added to the out strain, which is also not supposed to cause disease, as we see over here, realize that the bacteria, the out strain bacteria, the live one, develop the characteristics, the virulence of the air strain in order to cause the disease over here. Okay, so you realize that there is some kind of transformation going on. Okay, live strain, our strain here is being transformed to become a mutant, a wild strain. Okay, causing disease. So the house strain, which was supposed to be mutant, it is now developing the virulence of this heat-killed strain. There is something that has been transferred from the heat-killed strain into the house strain, okay, in order for it to cause the disease. And you realize that it also passes this trait onto subsequent offspring. Okay, when it develops this strain, the house strain ability to cause the disease, it now transfers it to subsequent offsprings. Okay, so this made Frederick wonder that what is this transforming material? What is it that is causing the live strain to transform, okay, into a virulent strain? Because initially it wasn't able to cause disease, but when it was added to the heat-killed air strain, it is now beginning to cause disease. So the question was that what is causing this live out strain to cause the disease? Okay, so that was the question. So in summary, what we have done is very simple. Okay, we have the strain of Connolly. Okay, for here we have the smooth strain, the air strain, or the wild strain. Okay, or the type 3 strain. And what it's doing over here is that it's causing disease in the mouse, causing the mouse to die. Okay, and here we have the strain of Connolly. Okay, which is the R strain. Okay, which does not have a capsule, so it's not supposed to cause disease. And truly, when it's injected into the mouse, nothing happens over here. So here in this section too, we have the heat-killed air strain. So we heated the air strain over here, and it's dead. So meaning it's not supposed to cause any disease. So injected into the mouse, nothing happened. The mouse continued to live. And in this last section, which brought up our question, okay, the smooth strain over here is heated and killed, as in this place. So under normal circumstances, it's not supposed to cause any disease, true. But when we add the R strain, okay, which is not also supposed to cause disease, okay, when we added it to the heat-killed air strain, okay, we realized that the disease developed in the mouse, which caused the disease to die. So our question is, what is causing the transformation in the live R strain, making it cause the disease? Okay, so in our next tutorial, we're going to look at what this transforming material is. Okay, we are going to look at other scientists, their experiments. Okay, and we'll come and we'll now see what this transforming material is. Okay, and I hope you like this video. If you like this video, you can just hit the like button for me, or you can also subscribe to this video. Okay, thanks a lot.